Hello everyone, today let's take a look at another combinatorics question, QP128, where we have this game called Chomp, where we begin with this 5x7 grid of cookies, and then two players are going to alternate turns. On a turn, the player chooses any remaining cookie and chomps it, meaning they remove that cookie and every cookie located above it or to its right. And in this game, the cookie in the bottom left corner is poisoned. The player forced to chomp it loses the game. So how many distinct board positions are there possible during the game? Okay, so essentially this is what we have here. We have our 5x7 grid of cookies right here. This one in the bottom left corner is going to be poisoned. And when it's someone's turn, they're going to basically eat a cookie, and whichever cookie they choose, they can choose whichever one on the map. They're going to remove all the cookies above it and to the right. So for instance, if they chose this cookie right here, well then all of these cookies would get removed, right? Then from this position, it would be the other player's turn. Let's say that they choose to eat this cookie right here, and in that case, we remove all the cookies to the right of it, of which there are none, and all the cookies above it. So it would look like this now. And then it would be the other person's turn. Maybe they choose to chomp this cookie right here, and in that case all of these cookies would get removed, and now we'd have this state of our board, right? And then maybe it's the other person's turn now, and they choose to chomp this cookie right here, and then in that case all of these would get removed, and etc. Then whoever decides to basically eat this cookie right here, the poisoned one in the left corner, they're going to lose the game. But it doesn't matter actually who wins and who loses. We're just trying to find the number of valid board positions, right? Okay, so now let's go back to the start position. If we start counting the total possible moves in a game like this, right, it's going to get very complicated because you can reach the same position when doing a different sequence of moves, right? You can reach the same position from multiple sequences of moves. So the question becomes, how do we describe basically a certain position so that we can count it, right? For instance, this position right here, how do we describe that? Well, basically the thing to notice here is that because we have this property where we remove all the cookies to the right and above a cookie that we eat, right, we're going to basically have this pattern where we have kind of these decreasing rows, or basically non-increasing rows, right? No matter what position that we wind ourselves up in, right, they're always going to have this pattern of basically non-decreasing rows, kind of looking like a staircase, right? Even if we have removed this cookie too, right, you see this staircase pattern here. You can never have a position like this, for instance, right, because now we have this hole here. If we remove this cookie, then the ones above it would have to been removed as well, right? This would be a legal position, but this one would not be. So we basically found this one-to-one correspondence here where the number of legal positions, which is what we're trying to count, is exactly the same as basically the number of arrangements of these cookies with this type of staircase pattern. So if we can count this, well then we'll solve our question, right? And then you'll just realize that every single staircase position can basically be quantified by a line going to the right, some amount of lines going to the right, and some amount of lines going down, something like this in this situation, right? You can see here that we've drawn 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 lines, right? And this uniquely identifies this position. And then if instead I was looking at this position, which is another valid one, then this sequence of lines right here would uniquely identify the position, right? And then right here, I basically have 12 lines again. Similarly, for this position right here, if I get rid of all of these, what's going to uniquely identify this? Well, now it will look something like this, right? If you imagine that I have a grid, I can just fill in basically all of these blanks right here with lines. So the number of legal positions, which we are trying to count, is basically going to have the same number of elements as the arrangements of these cookies with the staircase pattern, which in turn are going to have the same number of elements as basically the number of ways to arrange these 12 different lines. So the number of ways to basically arrange these 12 green lines such that they only go to the right or down, right? And we have to have these 12 green lines such that basically 5 of them go down and 7 of them go to the right, like they do in this case, right? These are our 7 that are going to the right, and then these are our 5 that are going down. And then if you'll notice, this is basically the exact same idea as QP number 31, the Manhattan commute, right? Where we're just trying to find the path basically from the bottom of the grid. That's what we're doing in Manhattan commute, from the bottom left to basically the top right when we have a certain size grid. So we can count this much the same way that we did in QP 31, right? In this case, I have 5 lines that I need to be going down and 7 lines that I need to be going right. So how many ways can I arrange 5 down lines and 7 right lines? So just like we did in that question, if you imagine I basically have 12 lines right here, then I can fill in each one with either an R or basically a D, such that I have 5 different Ds and 7 different Rs. And then this is just a multinomial problem, right? There's going to be 12 factorial ways to arrange those, and we have 5 alike and 7 alike as well. So 12 factorial on 5 factorial 7 factorial, also known as 12 choose 5, if we imagine that we choose our 5 positions for the down lines, or we could think about it like we're choosing 7 of our positions for the right lines. So that's our final answer right there. It's going to be 12 choose 5. 12 choose 5 is 792, so whichever way you want to write it, that's going to be our final answer. And that right there is going to be the number of valid board positions in this game called Chomp, right? So you can see that we found these one-to-one correspondences, right? So that we could count the set a lot easier, right?